to this area. Let's write that down. So the area of this rectangle, it's gonna be dt times vi minus vo. And this area is equal to 1 minus d times t times vo. Okay, so let's just like cancel the t's. This would tells us that vi times d, I'm just gonna, is equal, vi minus d, vi times d minus vo times d is equal to vo minus d times vo. Okay, so you can see that these two would cancel out, and then we end up vo, it's gonna be equal to vi times d, or I just like, if I just put it like in this form, vo over vi, it's gonna be equal to d, right? And this basically proves that the output voltage is going to be smaller than input voltage, and the ratio, it's going to be equal to the duty cycle. Duty cycle is always less than 1, right? This is d is always a number that's less than 1, right? So by changing the duty cycle of this switch, by making the period that this is on or off, we can change the output voltage, and this output voltage, it's going to be smaller than the input voltage, right? So that's how we can basically provide a voltage which is smaller than the input voltage on this side of the buck converter. So this is the voltage ratio of output voltage over input voltage for a buck converter. We did this using volt-second balance. This is an important relationship, but assume, like, you keep in mind that this is only valid if we are in the continuous conduction mode. If we are not in this mode, then this relationship is not going to be valid anymore. So we did all this analysis based on this assumption that the inductor current never reaches 0. It would basically never be 0. There's always current going through the inductor. I want to derive the same relationship, but from the current, inductor current perspective. So again, if you remember that if we are in the steady state, the current of the inductor at the beginning of the period has to be equal to the current of the inductor at the end of the period. So it means that the amount that we go up has to be equal to the amount that we come down, right? So what's the slope of this line? Slope of that line is 1 over L times VI minus VO, right? So how can I find this current ripple? This is called current ripple. So like how much we go up, right? If we have a line, if we have the slope, and we know like the time, if I multiply this by the time, this is gonna be our current ripple. So this is how much the current increases from this point to this point, right? If we are in the steady state, we have to also like come down the same amount, right? So if you look at this line, now if we calculate delta IL from this line, it's going to be 1 over L times VO over 1 minus D times T, right? There are two negative that are going to cancel because delta IL is going to be negative. In this case, there's a negative sign here. They're going to cancel out. So again, if we simplify this, let's just like cancel out 1 over L, let's cancel out T. And again, we come up with the same thing that we had before. VI times D minus VO times D is equal to VO minus VO times D. These two cancel out, so VO, it's going to be equal to VI times D. Right, so we can come up with this relationship from this curve or this curve. Both of them would give us the same thing. So this is basically the basics of buck converter in the continuous conduction mode. I want to draw some other parameters here. So let's look at the input current. If I call this II, or you can also like call it I switch, the current that goes through this switch, I input over T. So this is dt, this is T. Okay. How does this one look like, right? So when the switch is on, or this is closed, when we apply a gate signal to the switch, right, the diode is going to be reverse bias, so it's not going to conduct. So I input, it's going to be exactly equal to the inductor current. So it's going to have exactly the same shape that the inductor current has. So it would just like have this much current ripple. Okay. What's gonna happen after we open the switch, or like when we don't have any gate signal applied to the switch? It basically, there's no current because this becomes open. So this is gonna be the shape of our input current. This is gonna be important later on when we wanna analyze the circuit in the discontinuous conduction mode, but this is very trivial from the topology of the circuit. Okay, so that's related to the input current. Now let's look at the so we draw I input, IL. How about IC and IR? Okay, how about IC and IR? So one thing that we can see here based on the KCL at this node is IL is always equal to IC plus IR. If that's the case, it means that the average of IL is also equal to the average of IC plus average of IR, right? If we don't know why, so this is like what we have. Average of IL is equal to the average of IC plus average of IC plus IR, right? But these are two integrals, right? And you can separate them. So like this is how we can write this one. Average of IC plus average of IR, right? What's the average of the current that goes through capacitor over one period based on the amp second rule?